Assembly languages are the most fundamental instructions that a processor can execute, but they're incredibly difficult to become proficient in, and the instructions vary by platform. It would be much nicer if there was a way to just write code once and have it run everywhere. Fortunately, we have high-level programming languages to help us with this. Welcome to Hello World. Today we're going to look a bit more at assembly, but mostly at high-level programming languages, or HLLs. Now this video is not going to focus too much on the art and science of programming. There are already countless tutorials for that online. Instead, we're going to talk about what makes languages conceptually different from one another, and the general tool chain that one uses to make programs. A tool chain is just the name for a series of tools that take our human-readable code and turn it into assembly language. Now, as I said, I'm not going to try and teach you programming, but we will on occasion touch on some matters that are best presented with code, and in those cases I'll be using C++ because it's what I'm most familiar with. A little background on C++, since you may have heard of it before and are eager to impress your friends at parties. C++ is one of the world's most popular programming languages. It first came about in 1985 as the brainchild of Danish computer scientist. I'm going to cut in a couple different attempts to say the man's name. Bjarne Stroustrup. Bjarne Stroustrup. Bjarne Stroustrup. Bjarne Stroustrup. Bjarne Stroustrup. I think that one's good. It was originally an extension of the C programming language, intended to expand the language's capabilities in order to allow for more complicated and compartmentalized code while still maintaining the execution efficiency of C. In effect, it was thought of as a logical evolution of C, and even the name signals that. In C, is the increment operator, so putting ++ after a variable name increases the value of that variable by 1. Interestingly enough, C got its name because it was an improvement over an earlier programming language called B. And that language got its name from its predecessor, which was called BCPL. And while you're probably a little disappointed by that, take solace that you're not nearly as disappointed as any random computer scientist who happens to be watching this video and noticed that I glossed over 50 years of computer history in a few sentences. C++, as well as C, Python, and Java, the other heavy hitters of the world of programming, are all high-level languages. By this, we mean that they try and hide the down-and-dirty details of the assembly from us, generally by having a syntax that looks more like natural language. For example, anyone who's had exposure to algebra should be able to figure out this line of code. That's a valid line of code in every HLL I've worked with, assuming that you've declared y as a type that has or can be implicitly converted to a type that has a valid multiplier function, taking an integral second parameter, and x is a non-const type that can hold or implicitly convert the return value of that function. I mean, of course.
Alright, now let's compare that to the corresponding assembly code.
Yeah, I know. But hold on, I'm going to hit the e-brake for a moment here, because assembly has a reputation of being completely inscrutable, but in many ways it's very pure and direct. Because it's old, it's very structured. You only need to know a few concepts to start to understand. Give me a minute, and I can guarantee I can make you understand those 3 lines. Step 1, pretend you're left-handed. Bear with me. Also, your left hand is magical and it can duplicate things put into it. And your right hand contains some beans you want to duplicate with your magical left hand. Okay, step 2, now since your hands are magic, they're naturally going to have some magic names. When you see EAX, just think of that as your left hand, and D-word, PTR, whatever is just your right hand. Step 3, you move the beans from your right hand into your left hand. Step 4, you cast the add spell to add the contents of your left hand to itself. Bloop. Step 5, you move the beans from your left hand back to your right, where they originally were. See, that's all there is to it. Okay, now that you understand that bit of assembly code, let's break it apart a little bit. We learned in previous episodes that these words at the start of each line are assembly instructions, and the subsequent words are parameters, just extra information needed to perform that instruction. For example, if you're driving a car and I say turn, it's not very helpful. You'd probably rather I say turn left. The instruction is turn and the parameter is left. Every instruction roughly follows this format, though the number of parameters can vary. For the move instruction, we provided 2 pieces of information, the destination and the source. We talked about it as hands, but in reality it's locations or addresses in your computer's memory. A detailed explanation of what memory is and how it's accessed will come in future episodes, but the important thing to know about it right now is that it's just a contiguous range of bytes, like a file. The main difference is that memory is volatile. The data we hold there is only expected to persist for the length of the program. In older systems where a single program could run at once, you basically had the whole place to yourself and you could just put information wherever you wanted in memory. but each program in a modern multitasking operating system is allocated a small chunk of memory for working data, called the stack, and a larger chunk called the heap. As a result of this memory segmentation, modern programs have to know where their heap and stack start in order not to stomp the memory of other concurrently running programs. The start of the stack, which we're using in this example above, is represented by the EBP. Anytime we reference any data from the stack, we address it via an offset from EBP, as we see with EBP minus 4. The 4 refers to the size of the data type we're storing, 4 bytes, the reasons for which we'll come back to a little later, and the minus, well, the offset is negative because of computer science reasons that are more complicated than we need to go into for right now. The dword PTR part expresses the size of the memory allocation we want to make. In this particular assembly language, it's possible to allocate 1 byte, 2 bytes, a word, or 4 bytes, a double word, or a dword. The PTR in this case is what we call syntactic sugar, some syntax or text that we don't technically need but is often helpful to humans who have to read the code, a rare thing in assembly indeed. The last part to explain is the EAX, which refers to a specific part of memory the CPU can operate directly upon. For example, we can't do an add operation directly on the data at EBP minus 4. We have to put it into EAX to do the addition, and then put it back into EBP minus 4 when we're done. We call these special places in memory registers, and we'll cover them in further episodes on hardware. As I said earlier, when using an HLL or high-level language, we don't write raw assembly instructions. We use natural syntax, or more natural syntax. Each language has a part of the toolchain that translates the language's syntax into the correct assembly instructions. Broadly speaking, there are 2 types of languages, compiled and interpreted. Thank you to Nicholas Crosgrove for reminding me in the comments of episode 1 to tackle this. For a compiled language like C++, the code is translated by a compiler into assembly language and packaged up into a self-contained executable that you can run with as few as 0 dependencies on other programs. Interpreted languages like Lua or Python require that the end user have the appropriate toolchain installed in order to run them, because they are effectively compiled each time they're run. This means that programs written in interpreted languages are slower to start up, but since the entire toolchain must be installed on the running computer, you're able to more easily run your code on different instruction sets with fewer per-platform considerations, because the bulk of the considerations have been made by the people who adapted the interpreter to that instruction set. In the modern era, where we are flush with cheap memory and computing power, it seems obvious to make your programming language look more like natural language. But back when memory and computing power were precious resources, it made more sense to talk a little more directly to the computer. The fewer transformations that we force the computer to make when we compile the code, the quicker we're able to test our code and the better off we are. We're also able to be very specific about what instructions are getting executed, which, again, is very important when you don't have a lot of power to spare. Early programmers also didn't have the huge variety of instruction choices that modern high-level languages offer. They were essentially calling CPU instructions by name, and so their compilers just read the first word of each line and looked up which CPU instruction those letters corresponded to. Typically, those words were only 3 letters long. In general, you could rely on having operations to add, subtract, compare numbers, and jump to different parts of your code. Anything that was missing, you either had to design around or write yourself. Early programmers produced amazing work, especially considering the incredible constraints placed upon them. In addition to their limited instruction set, they also had limited memory to contain their program. So not only did they have to write extra code for decadent features like multiplication, they had to make sure they did it in the most efficient way possible, lest their program run too slowly. They had to balance this against the code having too many instructions, which would mean that the program wouldn't be able to fit in memory and therefore couldn't run at all. Although not all instructions are created equal, the general advice for programmers, even in the modern era, is to keep the instruction count low. Fewer operations is almost always more efficient. This is easier said than done, of course. Even for something as simple as multiplication, there are many ways a programmer could choose to perform a given operation. Take a simple operation like 3 times 8. We could do this, so that's 8 operations. But multiplication's transitive property means that we could do this in fewer steps. There we go, 3 operations. Shave that down nicely. Oh, but what about that fancy left shift we talked about in the first episode? The left shift allows us to easily multiply by any power of 2 by shifting the binary bits to the left. We can do that, and then just add the remaining 8. Now we're talking 1 shift and an addition. Just to being thorough, what if we swap the operands like we did earlier? Alright, a single shift operation. Now, we have a decent result, but it took quite a bit of time to get there. If you're thinking that we should get the computer to do this work, you're thinking like a programmer. The act of reducing the instruction count to increase runtime performance is called optimizing. And although many modern compilers do it automatically, it took a while to get where it is today. The first successful optimizing compiler is considered to have been developed in the late 1960s. The bar for success was fairly low at that time. It was considered a success because it could generate more efficient code than hand-coded assembly on average. By the 1980s, the increasing speed and quality of optimizing compilers meant that we were pushing many people away from hand-coded assembly. But even to this day, compilers remain imperfect, and as such, code is still occasionally hand-optimized in raw assembly. The main downfall is that automatic optimization is naive, depending on settings that either focuses on minimizing instruction count or minimizing code size, regardless of other conditions. Take this contrived scenario, for example. Let's say you're working on an embedded system of some sort, and are optimizing for performance because you want to maximize battery life. You have an operation that uses a lot of instructions and is needed all over the code base, so you make it a function. Good practice, right? Write it once, reuse everywhere. You kick off the build. The compiler sees you're optimizing for performance and says, hold up, they're calling this function a lot. And it's an overridden virtual function that's not marked final. They're going to incur a ton of performance hit from V-table lookups. This is like a good spot for inlining. I'll copy the bytecode from a function and duplicate it in every place where it's called. Oh man, they're going to love this. The next thing you know, you try to copy your executable over to the target device, and it's out of memory because your code size is bloated up with all those duplicate inline functions. Optimizing compiler! Still, the cases like that are rare, and the tricks that compilers can do are incredibly clever. Take our 8x3 example from earlier. In all our attempts at optimization, there's one incredibly simple thing we didn't consider. Evaluate 8x3 compile time and just replace it with 24. Check it out, 0 additional operations. Compilers allow us to reap the benefits of not only fast modern CPUs, but also the decades of optimization research by the greatest minds in computer science. When you compile, you are standing on the shoulders of giants. And let me tell you, the view from up there, highly optimized. High-level languages have a lot going for them. Their power and ease of use have made programming more accessible to people who ordinarily might be scared away from the unforgiving terseness of assembly. But at the end of the day, no matter what programming language you use, or what web browser you use, or what word processor you use, all of it relies on input from you, the user, to get anything done. Without you there to provide input to the computer, it has no purpose. Join me as we learn how all these keystrokes and clicks get turned into data for programs to use on the next episode of Hello World.